Hi, my name is Mads Jespersen and I'm from FlowHow. In this video I want to show you some of the results that you can get from PU foaming. So I made a run and the first thing I will go into is the filling, and if I go to results here, you can see if I go back and forward nothing really happens. I changed this for single color. But if I right click here and choose the last calculated steps after the filling, my filling is 8 seconds, so this one 14 is the last. Then I have the possibility to look at the filling. I'll just get rid of these probes. So as you can see, the filling is going up here, and then it fills out, and the gravity is set minus, which are dragging the melt downwards, and then you have like a splash of yeah, not water but material going up and surrounding this. So maybe it's not that clever to have a runner like that and place here. Maybe it should be placed out here. Another thing I'm looking at is, of course, the air traps. Where does it end? But also well lines. But now I jump to the end of fill results, and then I can look at the temperatures. These are the surface temperatures, but if I use clipping, I can see other what is the temperature at a certain time step. This time step is 406 seconds, but if I click here, I can choose different time steps depending on which time step you have asked for in the computation when you set up the analysis. Um, Specific for PU foaming, I think density is quite important. And if you're in doubt about a result, you can double click the result. I do it like this, and you get a distribution of the density all over the part down here. Of course, you can adjust that if you want to see, how much do I have between 0.5 and 0.6, for example, like this. And you can see uh, the distribution of the melt of the part in here. And then we have the conversion, which is the conversion, not foam conversion, but total conversion. And then we have the foaming conversion, which is the conversion of foam creation, you can say, and reactive heat, viscous heat, reactive heat creation, viscous heat, which is very low in a low viscosity, cell size, cell density. These are the most common. And what I'm using a lot is, for example, this is to one certain time step, but if I want to look at the maybe foam conversion over time in these probes, you can see here I placed some probes here. Then I can go into the history plot and say, how is the conversion doing here? Oh, I'll just say probes like this. not melt front, but conversion, foam conversion. And then I can see how is the foam conversion or the foaming actually accelerating in these areas, these two specific areas. We can get rid of those. I can close here, but I'll just try differently. Delete those, and instead of foam conversion, temperature over here, and you can see how the temperature is developing. Probe 1 is the outer one, it's going up but cooled down quite fast. The other one is heated up due to the chemical reaction inside at the heat creation. So you get a more, you get a higher um, temperature at the top level. So these are some of the most important results that you can get from the PU foaming. And of course, when you then change the gate position, you can compare and say, okay, I want a more uniform density, for example. Can I change that only by changing the runner, or should I change the part? So that's the good about simulation, that you can predict everything before going into the final investment.